Okay, so we are live right now. So we'll be talking about facial detection, recognition, and verification. Right. So let's just break this down. What is facial detection? So right now, there are two of you in this chat. So I can recognize your faces. Right. I'm able to recognize Osun and Arvind. Osun and Arvind. Right. Osun Arvind, then who joined the chat right now? I'm not able. Prasanna. Right. I'm able to recognize your faces. But that is like I'm able to see your face, but I didn't know your name before that. So I'm able to see your face. That is facial detection. Now, facial recognition is I see your face and then I know your name. That is facial recognition. So that is the main difference between facial recognition and facial detection. Now, what is facial verification? Right? So if you go to office complexes, what often happens is that you have to show your ID card and then you have to show your face. So the camera tries to match your face with the face in the ID card. So that is known as facial verification. So before continuing, I just want to make sure that the difference between these three concepts is clear, right? Is it clear? Is it clear? Right? If you have any doubt, please ask me in the please ask me in the comment section, right? So first of all, um, we'll start with facial detection, then we'll slowly proceed to facial recognition. So the format of the webinar is going to be I'm going to walk you through a Jupyter notebook, right? Where I have I'll walk you through a Jupyter notebook where I've written some code, and then I'll explain you what the code is doing. And then in between, we'll switch to the theory part. So I'll also teach you the theory behind what is happening. So how are we detecting faces and how are we recognizing those faces, right? So the first thing, which I know, if you would have done this core, if you would have done this course, you would have realized that whenever you're training a neural network, right, you have to need a lot of data. So for example, if you did the data set cat dog data set, you would have realized that if you had done the cat dog dataset, you would realize that there are a lot of images that you need of cats and dogs. But that is not the case when it comes to humans, right? I mean, if if you show me a new species of animal today, 3 4 photos, I'll be able to recognize it. So in that way, modern machines are not able to match that level of human intelligence. So the same concept applies to facial recognition also. So for example, I saw you guys right now, and if I see you in another webinar, I'll be able to recognize you very easily because I just saw your face immediately, and then I don't need a lot of training data. Like I'm not asking you that you send 1,000 pictures of you to me, and then I'll be able to recognize. So this is something that researchers saw, and they thought that uh, this is something that researchers saw, and they felt that this is what we should our modern machines should be able to work on very less amount of training data. That is, they should be able to generalize, right? So this is we're going to discuss a paper called Facenet, which brought in this idea. So okay guys, so I am sharing my screen right now, right? So if you have any problem in the between, put it in the comment section, or otherwise I would suggest that when the webinar is when I end my webinar, you can all put your doubts, right? I will clear it because between if you put your doubts, I won't be able to see them, and then it will cause a little bit of confusion. So in the end, I will give you time to clear your doubts. So right now I'm sharing my screen. Okay. So let's start with the notebook, right? So this is the notebook. So we're going to run through this algorithm here, right? Which involve of what we are going to do in today's webinar. So first of all, how are we going to carry out facial recognition in using OpenCV in Python? So first of all, of course, import all the necessary libraries. So here are the libraries, right? NumPy. NumPy is obviously a very famous library which is used for all mathematical operations in Python. So Matplotlib. Matplotlib is basically a plotting software, right? So you can plot your graphs. You can plot a lot of graphs. You can plot images. So we'll be mainly using Matplotlib to plot images in this, and then OpenCV. So right, CV2. So CV2 is basically OpenCV, right? So for this is a special that I would like to say, for, especially for Mac users, uh, it is better to install OpenCV using Homebrew, right? And for other people, you can easily install it using pip. But I've found that in Mac, you have to use Homebrew to install OpenCV. So that is one thing that you need to take care of for Mac users, especially. Other users, you can use pip install or conda install to install OpenCV, right? So now let's come to the first part of this step, right? So here we imported all the necessary libraries. Then then the second part is loading images through OpenCV and cropping the faces out of these images. So just let me walk you through this code. Okay, so here we are, right? So guys, tell me if you're not able. Just say if you're not able to uh, hear something or do something. Just write it in the chat box. I will see it. Okay, let's go through this. So these are some images that I've collected, right? These are some images of world leaders that I've collected: Barack Obama, Donald Trump, Hillary Clinton. Then I've collected one photo where we have both Barack Obama and Donald Trump and Barack Obama in the same photo. So our final aim would be to perform facial detection, that is, detect both these faces and label these faces, right? So this should come as Barack Obama. This should come out as Donald Trump. Okay, so that is going to be our aim. So let's start. Wait a minute, let me just make this. Okay, so first of all, we have to read these images, right? We have to read these images. So for example, and then we have to read these images and convert it into a NumPy array, right? You have to convert it into a NumPy array. So if any of you guys have read about CNNs, you will realize that CNNs take in NumPy arrays. So this imread function, what it basically does is that it reads this picture, it converts it into a NumPy array, right? So let's go about this. Hmm. And now what is happening here, right? So this is another function in OpenCV, which is basically a convert function. So what is this doing? This convert function is basically converting the color image into a grayscale image, right? So if you would have been progressing through the PyTorch course, you would have seen that any RGB image contains 3 channels, while a grayscale image contains only 1 channel. So basically, this function is trying to reduce the channels to 1. And so we are doing the same for Donald Trump, right? And again, we're converting that into another grayscale image. We're doing the same for Mrs. Clinton, and we're converting that into a, a, a grayscale image. So let us just run this cell and see what is happening, right? So this is another function that is used in OpenCV. So IMShow is basically image show. So it shows you the image in a separate window by the name of window 1, and it will show you the image of it will show you this image, right, which is the black and white image. And wait key is basically, after this window is displayed, right, you have to come out of that window. So in order to destroy that window, you use what you click any key. So you have to wait till that key is pressed. So that's why we use this function of OpenCV. So let's just start, right? Okay, so let's go here. This is so this is a black and white photo of Mrs. Clinton. And as I go, you can see that these pixel values here, these pixel values here, they keep changing, right? This is a very good feature of OpenCV, that you can go around and you can see what pixel it is. Another um, concept that I would like to draw attention to is that you look at this part, right? It is 0 comma 0 here, somewhere here. What happens usually in a coordinate system is that 0 comma 0 starts from this side when we are drawing it, but for a computer 0 comma 0 starts from this side. So remember this. This will come in the future. This will be very helpful, right? This will be quite helpful when in the future codes. So now let me press the key. So you see this gets paused, and we come out of. So this is a problem that I face in Mac OS, that this gets paused. So you might not face it in other operating systems. So we paused, and then you have this command here which says that it has been executed. So Hillary image, I should just show you right now. Now let me come to the second part, right? Haar cascades. So let's start with the first part. We have loaded the images using OpenCV, and now we have to crop these faces out of these images, right? So how are we going to crop the faces? So we basically need a function, right? So you look at this portion of Mr. Obama, and we need a function which gives us a bounding box, something like this, right? So that we can crop out Obama's face. Uh, for Donald Trump, we need some function like this, which can crop out Donald Trump's face, which can give us. So what is this? This is basically a rectangle, and we need the coordinates of this rectangle, right? So in order to find the coordinates of this rectangle, we use what is called as a Haar cascade, right? A Haar cascade. I'll walk you through what a Haar cascade is, right? So this is something that I found on the net relating to Haar cascades, right? So basically, Haar cascades, each there are about 60,000, there are about 6,000 features in our face, right? For example, you have the eyes, you have the nose, you have ears and all that, you have hair and everything. So we take a image subregion, that is, we take some portion of the image, like we take this image, this portion, then we pass it to the first feature. Then we try to find out if that feature exists or not. If there is a probability that that feature might exist, then we go to the next part. If that feature does not exist, then we exit the loop. We do this until all the 60,000 features are checked. So any rectangular box which satisfies this, all the 60,000 features, all the 60,000 features is going to have, it is going to have, it is going to be a face. It is most probably going to be a face because it is satisfying all the features, right? So now let me walk you back. So what is happening here, right? Now see, face is cascade equal to cv2 dot cascade classifier. So what is happening in this is that, so how many of you guys have done part 5, part 5 of the PyTorch intro, PyTorch intro, right? Okay, you haven't finished. Yeah, you are right, Prasanna, you are right when you say that it can be easy for you. You can custom, you can also train your own Haar cascade, or actually, if you go on the net, a lot of um, a lot of Haar cascades are available. So you have to just find the XML file. I'll just say what the XML file is in a few moments. Has anyone got any doubt? Any other doubt? So okay, so in the fifth chapter, what do we do when we train a model, right? We save it in a checkpoint file. So in the same way, when we train a Haar cascade, we have to save it in a XML file so that we can load it later, right? It is very similar, right? Very similar to PyTorch framework, that in PyTorch we use a checkpoint file. In case of Haar Cascades, we use a XML file. So that is what I have done here. Right, I'm starting my screen sharing again. Guys, if you have any doubt, just say it in the comment section. Okay, no problem. Okay, so that is what I'm doing right here. Right, okay, uh, I am taking my this is the path to my XML file. So you can see what it says here. Frontal face default. So this is the default XML file for a frontal face. In fact, if you once you install your OpenCV, you will find that this is all these cascades already come built into your OpenCV application. So you can, for example, you can see here there is one for right eye, two splits. This is one for your um, eye, right? This is one for your frontal face extended. So there are a lot of XML files, and you can find XML files online also. And yes, like Prasanna was saying, that you can also train your XML files. You can also train your Haar Cascades and store them in XML file. Just let me just show you how this looks. Right. So this is the XML file. Just like PyTorch, you can see that there are numerical values, there are nodes, and it's a very big file. Like it is almost like 30. It's like 25,000, 25,000, 25,000. That's pretty big. Let me come back to the webinar. Back to the notebook. So I've loaded this HTML file. Right. Are you guys following me till here? Let me just 1 minute. Okay. Guys, is there a problem with my screen? Wait a minute. Wait a minute. Oh, sorry. Oh, I'm sorry, guys. I'm sorry for that inconvenience. Right. I'm dreadfully sorry. Uh, I didn't click the share button. Okay. Is it okay? Is it working now? Guys, please write it in the chat section. Is it working right now? Okay. Okay. Yes. Okay. Okay. So where was I? I was explaining XML files, right? So so let me just come back. So have you guys understood Haar Cascades? Haar Cascade. Okay. Okay. Haar Cascades. XML files. XML files. Okay. I'll show you the XML files. Wait a minute. So these are the XML files. Okay. So just like in a checkpoint, what we happen is that we train a neural network and we store it in a checkpoint. We train a Haar Cascade and we store it in an XML file. So this is XML file for Russian number plates, right? It's quite a long file. You see there is a lot of numerical values. The same way that we store weights in a checkpoint file. Same way we store weights. So these are basically values of filters, which values of the features that we are going to use in our Haar Cascade. So there are a lot of Haar Cascades, and you can download these Haar Cascades from online. You can download these XML files online, right? If it's not available in OpenCV. So have you guys understood XML files? XML files, okay? Okay. Okay. I know it's becoming a little bit difficult, but just adjust with me. It's the first time I'm using Hangouts. So, okay. Now I load this XML file. Just like you load a checkpoint file, you load the XML file into any variable. Right. We load the XML file into any variable. And then we call a function called detect multiscale Barack image. So this is the image of Barack Obama, which has been converted to grayscale. So this is very important, guys. Whenever you are performing this operation, convert the image into grayscale. Otherwise, it won't work. Very simply, it won't work. So I'm doing this for all the people, right? Obama, Hillary, and Trump. So now let me just say what these parameters are, right? You're seeing a 1.3 and you're seeing 4 here. Then you're seeing 1.2 and you're seeing 4 here. So 1.3 basically, now let me just come back to this. Now, when we were passing from one feature onto another feature, what generally happens is that the image is scaled down, right? So this basically represents the scaling factor. So if it's say zero point 0.3, right, it will scale down by 30%. If it's 0.2, it will scale down by 20%. If you go down, it's written here, right? It specifies, this is scale factor basically. It specifies how much the size is reduced at each image scale. For example, if you have 1.03, it is reduced by 3%. So it is, you have to, sometimes what happens is that uh, you don't get it in the first attempt. So you have to configure this rightly so that you get those values. And now let's come to this part, 4. 4 basically, this is another question, I don't know if this popped into your head or not. Say this is one photo of Mr. Obama. This is one, right, bounding box. Another bounding box can be this. You can also have this as a bounding box, right? You can have multiple bounding boxes for one face. How are you going to, so you can't give all the bounding boxes, right? You can't give all the bounding boxes. So what you have to do is that you have to select only one bounding box. So this 4 tells us how much bounding boxes we have to select, right? This bounding 4 tells us, so if it's a 4, for example, I take a bounding box here, and then if I have 4 bounding boxes here, then this will be selected, right? Otherwise, if there are only say 3, this won't be selected. This will be rejected. So the more you increase the value of 4, the more amount of bounding boxes there need to be. So, and what does it mean by more amount of bounding boxes? It means that it is very precise, right? Because the same sub-region is giving you a lot of bounding boxes. So if it's giving a lot of bounding boxes, means it is satisfying that. Just to increase your precision, you can increase this, but sometimes, even some minute images are neglected. For example, if someone's face is small, then you don't have much bounding boxes, but it is still a face. So you have to configure these two parameters according to how it is, according to if it's detecting a face or not. Let's just go forward and run this. You see 4, so say Obama face, right? So this is, I've stored Obama face. So let's see what is this returning to us, right? So let's just see what is returning to us, right? So I'm going to run this function and I'll tell you what is happening in this. Okay, good. So this is, see, window 9. Wait a minute, guys, I'm sorry for inconvenience. So this is window 9. Window 9 is what it is running here, right? Window 9 is what is running here. And then we say window 9 display the color image of Barack Obama, right? And I just told you what wait keys means. And now let's see what's happening here. X1, Y1, W1, H1. So you can see that this is a quadruple, right? This is basically an array consisting of quadruple values. So I have just equal, so X1 will be equal to 23, Y1 will be equal to 25, W1 will be 81, and so on. So this is basically quadruple. Obama face basically returning a quadruple. Now, what are these values? So say 23 and 25, X1, Y1. What is 23, 25? Let's go and see here. Can you see it? It is basically the left upper corner of the bounding box, right? It is the left upper corner of the bounding box. So x1, y1, the first two values are basically the x and the y values of the upper left part of the bounding rectangle. Now let's come to w1, right? W1. Now guys, just measure this. This is 24 and this is 104, right? So it comes about 80. What is the value here? 81. So 81 is basically the width of the bounding rectangle, and conversely h is the height of the bounding rectangle. You can check it here, right? So this is say 27, and this is, you can see it is almost closer to, 81. So just remember this. First, xy coordinates of the left upper part. The second will be w and width and height coordinates, width and height of the bounding rectangle. So how are you going to calculate the, so whenever you're constructing a rectangle, right, you need two coordinates. You need this coordinate and you need this coordinate. Now I've given you the width and the height. How are you going to construct this coordinate? Right? Anyone, the chat section, who can, is my screen share is working, right? Oh, okay. Uh, mm, okay. You want me to share the? Actually, I have not uploaded this on GitHub, so it's going to be a little bit problematic for me. But I will do it after the um I will do it after the session. I should have uploaded uploaded on GitHub earlier, but if you're not able to understand anything, just write it in the doubt section, right? I will surely put the code on GitHub, right? Then we'll go. So, are you guys having any problem with following along? Acha, that you want to understand how we are combining to get a rectangle. Okay, okay, you understand it. Okay, no problem. So guys, oh, okay, okay. So yeah, sure. I mean, you guys can chat yourself in the comment section also. I'm not able to see the comment section because I'm sharing my screen. So okay, let's start. You're able to see my okay, sharing my screen. Let's go. So okay, so you've understood it till now, that how we are. So now see, this is a function which is used to plot the rectangle on top of the image. So what is this saying? It is saying plot a rectangle whose left upper part is coordinates are x1 y1, and whose right bottom part are x1 plus w1 y1 plus h1, and plot it on this image with this color scheme, having this this thickness, right? Having this thickness. So it is quite thick. You can see, if you vary the thickness, then it will decrease. The thickness will decrease. You can change it according to whatever you want. So let's just press the key. Yeah, okay. So this is done. See, it is executed. It has returned me the value. Okay. So guys, I've completed with the point of face detection, right? I've completed with face detection. Any doubts about face detection? How we are detecting face, how we were drawing the bounding rectangles? If any of you have any doubt, you can ask. Or if I'm explaining it too fast, or if you're not being able to clear, if it's not clear, because even I'm not a very good teacher. Should I continue with the part? Okay, okay. So now we have detected faces, right? So first task is complete for us. So Prasanna, even I I don't know how to do that, right? Because I use custom made XML files only. At least till now, for the computer vision applications, I've used uh, I've used the XML files. I've found them online. You can you can search for them. Otherwise, after this, after the webinar, I'll send you some links. So on how to train, how to make your own XML file, because even I don't know. Uh, Frankly, you if frankly, a lot of them are available on the internet if you search for, unless there is a very specific use case that you're trying to do. Because for example, I did one using where I had to detect cars, and I had to detect license plates. So I found the XML file for that. So you know, I will, after this I will search, and I'll send you some links. So guys, should we continue? Right, first first part was facial detection, right? I've detected the faces. Now I want to identify it, right? For example, I'm seeing Ocean here, right? So I see his face, but now I have to identify him as Ocean. So now how are we going to do this, right? Now that the second part of the presentation is regarding that. So what do we do in case of, so say for example, I saw a person for the first time, then you remember that face for a very long time, right? So when you see him next time, uh, you recollect immediately, right? So we want to train a neural network which will do exactly that. We just sees one image of that person, and it says that, okay, this person is this, or this person is this. So that is what was a very major problem which was faced by researchers when they were trying to find a solution to this problem. So a paper came out called Facenet, right? So Facenet is a paper which gives you a neural network, which gives you a neural network, which gives you a neural network to help you solve this problem. So it is a very, very, very different kind of neural network. So let me just, so okay, I'm sharing my screen again, guys. Are you able to see now? Okay. So let me just go to these slides. Okay. These are not my slides. So this is something called as a Stanford Scholar Initiative. So what generally happens is that you enroll in a group, then you guys get together in a group, and then you prepare a presentation on any research paper. So this has been done by a few students. You can, this is not my presentation, Florian and Dimitri and James. So let's just walk through this. Okay, right. This is the state. So see, this is what we were talking about. Why it is respond why it is very important that it is to create a machine which is, I was telling you in the starting of the session, that it is very important that the machine just thinks like a human and some other. So now look at this. This is very, this is what I was talking about. That why is it very hard to perform facial recognition? So first of all, I'll talk to you about the fifth point, right? So for example, when we are a face, right, it is not possible that one's face is straight. It can also be tilted, it can also be upside down, but we still recognize that a human still recognizes that that face belongs to some person. But in case of machine, in fact, when you will see when you're training CNNs, you will see that if the dog's face is a little bit rotated, right, and you have not trained your CNN on rotated images, it will not recognize. So this is a problem which persists with neural networks, is that they are only able to perform on datas which are provided to them, right? So this is, for example, they fail when there are a number of objects in an image and there is some form of rotation in them. Same thing. And another problems with uh, image recognition is that you can have low resolution, right? So we have different cameras. So people have different megapixels, and it should not be the case that someone with lesser number of megapixels is not able to, the machine is not able to identify faces. So that should not be the case. These are some of the problems that are persistent. So this is, let me just go embeddings, right? What the main topic of this, what is an embedding, right? So embedding is basically, say you have a 200-degree vector with you, right? 200-degree vector. Can you represent it in space? You have a 200-degree vector with you, right? Can you represent it in space? Not able to see the chat. Right. Yeah. Yeah, Ocean. You'll not be able to represent 200 degrees in space. Now, how do you? But if I want to do a visual analysis of, say, a lot of vectors and their 200 dimensions, how do you do that? I have to convert those 200 vectors into two. I have to convert that vector. Yeah, yeah. But the graph is only 3 dimensional. Is only 2 dimensional, right? It is not 200 dimensional. So you convert those 200 dimensions into the two dimensions, right? And how do you convert those 200 dimensions to 2 dimensions? Can anyone guess at how are you going to do that? Okay, I'll tell you. Right. Yeah, you're very close. Yeah, you can use a convolutional kernel, but the convolutional kernel is specifically for images. So, like, you can use a convolutional kernel. That is, yeah, that is right. For images, you can do that, but for, say, 200 vectors, you can also use a dense network. And input nodes will be, how many input nodes will be there? 200 input nodes and 2 output nodes, right? I'm not coming on the training part because then it will stay. Just say that we're able to train it in some. There is a method called autoencoder which we use for training, but just say that we are able to train this network and it is able to convert those 200 vectors into 2D vectors, right? So that they can be represented on a graph. And what is this 2D vector? This 2D vector is basically a low level representation of that 200 dimensional vector. So, say for example, I'm sharing my screen again. Okay, okay, let's start. So, say for example, now you can see it here. We have basically, what we have done is that we have taken some photos and then we have converted. We have unrolled the pixels. So, say this is a 24 into 24 photo, 24 24 into 24 pixel photo, and then we have unrolled, we have ran a convolutional kernel to it, and the output nodes just have two dimensions, right? It's the same concept. Just think that uh, the number of dimensions is equal to the number of pixels of this image. So truck lies here, bird lies here. So you can see, let's say for example, airplane, a ship, and an airplane. Both of them have are similar because both of them are uh, modes of transport. A truck and automobile are similar. Then you can see here bird, frog, cat, dog. So this is somewhere around non-living objects in this side of the screen. I will put a pointer. In this side of the screen, you have non-living objects, you have modes of transportation. In this side, you have uh, animals, right? So you can see, for example, cats and dogs. You can see there's an evolutionary relationship. For example, you have frog, then you have a bird, then you have deer, you have horse, you have a dog, you have cat. For example, these two are grouped together because they are similar, right? They are domesticated animals. So this actually helps us in studying the relations between those high level vectors, right? Which you cannot do in the high level representation. So when you convert them to a lower level representation, you're able to easily study these vectors. So now think of it in the manner of an image, right? So for example, I told you how we are cropping that image using a rectangle, right? So what can I do with that rectangular cropped image right now, right? So what can I do? Can I convert it into a lower dimension? Can I convert it into a lower dimension? Yeah. Exactly. You can convert it into a lower dimension. Just like you were saying in the earlier part, your, what do you say? Your cat and dog were similar. So if I take two photos of the same person, convert it into a lower representation, will those vectors be similar? Yeah, you can make it a 1D. Exactly, right? This is the concept of a facial embedding. Yeah, it will be similar, right? If I take another person, if I take another person and this person's so there's a target image, I convert it into the lower dimension, then we have two images, right? We have two images, we convert into lower images, a lower representation. Then we compare these, right? And the one with the which is closer to each, which is closer to one another, is the one which is very similar. It will be seen as a shape. No, we are pixels are very. I didn't understand your question, Prasanna. What I'm just saying that, are you able to understand my concept that, say for example, you have a higher level representation. Oh, okay. Yeah, so it will be seen as a shape alone. You're right. That is also. So in that case, I mean, he's right. Prasanna is kind of right. If s- the neural network that we're going to talk about works in all kind of conditions, because it is trained in a manner. But if you're training your own network, then it will become a little bit difficult. So what you need to do is that you need to apply some operations using OpenCV. So you need to brighten that image. Yeah, okay, that you can do that, but I will tell you about the library which has all the required neural networks for Facenet in this exercise only. Right. So are you able to understand my concept that if you're able to convert all the images in the universe into lower level representations and find the similarity between them, the one with, so for example, your image will be more similar to the lower level representation of another image of yourself. That is what I am trying to convey. Right? I hope you've understood, right? So if any of you guys, if you're not able to understand, yeah, okay, okay. So guys, if anyone is asking you for the link, right, just send them, because a lot of guys were asking me for the link. It became a little bit problem in the end. Okay, I'm
Hello,
sharing my screen again.
hello, sir.
Yeah,
I don't know if I am happy to join this session. I don't know if it is advised to, because I checked for the message box, but I don't know if it's advisable for me to ask you questions during the live streaming. Is it?
look, I what's your name?
My name is Bai Gaspat. I am
Okay,
presently uh,
okay,
in
okay.
Cameroon.
Guys, I'll have to
This is
mute you for a moment because this is a webinar, right? I will unmute you after I complete my webinar. We can have a very thorough discussion about the doubts, okay? Because it's a webinar, right?
thank you.
Yeah, no problem, right? I'm sorry, but they've instructed us to, first complete the webinar, then we'll have a thorough discussion. So you guys are able to understand this, right? That we can convert. So that's what is Facenet is basically is doing. I'm starting my screen sharing again. Okay, let's go. Let's see what's happening here. See what's happening here, right? What is happening here? Now, how are we going to train this neural network? That is the main question that you have to ask. So we have a photo of Barack Obama here, a photo of Barack Obama, and we have a photo of Emmanuel Macron. He's a French president here. We pass it through a CNN, and then we take out the embeddings, right? These are 128 vector, so images represented by 128 dimensional vector in the Euclidean space. And these are calculated by passing it through a neural network. Same, we do it for, so just keep these three images in mind: the anchor image, the positive image, and the negative image, right? So we pass it through a CNN, we take these embeddings, the embeddings for all the three images, and now we have to design a cost function, right? So please tell me, how many of you guys don't know what a cost function is? You know what a cost function is, right? All of you? Okay. Good. Okay, cost function, basically, Prasanna, cost function is something that you need to minimize. So if you progress through the course, you'll know that in so for example, you need to, for when you're predicting a neural network, right? So you need to minimize a cost function, and then you need to back propagate through the network. So it's uh, wait a minute, I'll just, okay, here it is. So cost function is like your marks, right, Prasanna? You have to, in case you have marks, you have to increase your marks. Or let me take the example of rank in your class. So you have to decrease your rank in the class, right? And how can you do that? By learning more and more, by studying more and more, right? The cost function in this case is your rank, and you studying more and more is basically a learning process. What happens? You give your test, you get your rank, and then you realize that your rank is low. Then you realize that your rank is low. Then you realize that your rank is high in the class, and you go and study again. Then you secure a better rank. So this process keeps on continuing until you reach a pinnacle, right? So same is what we do in case of a loss function, that we we make, we propagate through the network, then we find the cost function, and we minimize, try to minimize that cost function by altering the weights of the network. Yeah, Osun has put this. You can check this out thread. A lot of threads in our Slack channel. You'll understand it. I'm starting my screen sharing again, guys. Okay. Hmm. So now what's happening here? So this is a cost function. So now you have to design a cost function for this. So let's just start with the rank analogy. We take an embedding of the anchor and we take an embedding of the positive image. And these two embeddings have to be similar to each other, right? That is, if we find the difference between these two vectors and we take their magnitude, right? Are you able to understand what I'm saying? Are you able to understand by difference of the vectors and their magnitude? Okay, okay. If you're not able to understand, tell me. I'll explain. I'm basically taking difference of two vectors and I'm taking their magnitude. That's all. This is a 128 vector, 128 vector. We take their difference, we square them, and then we divide them by 128. Okay. What what has to be the value? This value has to be very small, right? This value has to be very small. In an ideal neural network, you know, these values have to be small. And when we take a photo of when we take the embeddings of Mr. Macron and we take the embeddings of Mr. Obama, and then we again do the same. We differ them and then we square them, add them. That is, we take their magnitude and we divide them by 128, which is the size of the embedding. These two embeddings have to be very, very large, right? The value of the difference, the value of the magnitude of the difference has to be large. So can you understand? Can you say how are we going to design the loss function? Anyone? Anyone? Yeah. So Ocean, mm, yeah. So you are a little bit, you close, but so what is he's kind of right that we'll add the yeah, yeah. So he's saying that we can subtract the output. So what we will do is that we'll take these two embeddings, subtract them, take their magnitude, right? So if these are small, then our cost function should be small, right? If this is small, say if this is small, then of course our cost function will be small because this is the ideal situation. And if this is large, then our cost function will also be small. Why? Because this is the ideal situation. We don't want these two, we don't want this and this to be similar. So what we do is we take the difference of these vectors and we add it with the difference of these two vectors, the magnitude of these two vectors, right? That is, we take the similarity between these two vectors and we subtract it with the similarity of these two vectors, right? So you can find it here. What is this? This is your anchor image. This is your positive image. We take this function is basically your embedding, right? So you're converting it into a lower dimensional representation, the 128 vectors. And then you square them. And then you subtract it by the difference of the positive and the anchor and the negative image. And then you square them again. And then you add what is an alpha value. Why do we do that? We do that because the entire part should be should remain positive. That's why we add alpha, and then we sum it over all the images, right? So this will be our cost function. And anyone who's not been able to understand the cost function, so tell me if you're not able to understand the cost function. Okay. Anyone else? Prasanna and Gas, Arvind, any of you guys? Hmm. Okay. I mean, you're able to understand the concept behind the cost function, right? So this is, I mean, you don't need this much theory, but I'm trying to make sure that your concepts are clear, right? Okay, okay, good, good. Let's just continue again. So what do we do? So does this remind you of something? So any of you done the PyTorch? Did you do the neural net style transfer? Any of you have done that lesson? Yeah, a similar type of representation in that also. We don't have subtraction and all, but in that also, when we are trying to do it for the content image, the same way we subtract and take their squares. So and then we back propagate through the network. So that is what is being done here, right? To train the network. Let's just go. Okay, so now this I mean this when I read this idea, it is really an amazing idea. So it's what is called as a triplet loss function, right? Because we are usually we take only two. This time we are taking three images. That is really amazing. So this is the category of the CNN which is being used. It has convolutional layers, and so Google Net is basically a very it is used by Google, right? It is a very deep model, but it is quite a deep model, but still it has fewer parameters. So embeddings done. So why this was very good, right? So there's this data set called label faces in the wild. So it achieved almost 99.7% accuracy, and it achieved 95.12 accuracy on the YouTube faces. It's good. And I mean, this is really amazing. It has decreased the error rate by 30%. So I mean, that 30% is like a very good number, right? And in fact, this is I think all the modern facial recognition systems use this only. There is no other accepted standard in the industry right now which gets closer to this. So, I mean, you can come out with one if you're going to do research in the future. Like, you can beat this, but till now there is no. This is some of the same achievements. This is thing that is there. I will send the link to this slide. And I will also send you the link. Oh, sorry. Again, did okay? I'm doing it again. Sorry. I'll do it again. I'll do it again. So yeah, this is where it happens. Data sets. So these are two main data sets, right? So it is evaluated on label faces in the wild and YouTube faces. So you can see the accuracy. It's quite high. I mean, this is a very good accuracy, and it has decreased the error rate by 30%. Like, that is a very good standard. And I think this is used in the industry right now. It is the mostly used. I mean, in the future, if you're able to design a better technique, that's good. It's the same thing, right? So this sums up our theory regarding how we are trying to do face recognition, right? So are you guys able to understand how we are doing face recognition right now? Facial recognition, right? You understood the concept of embeddings, the concept of how we are converting them into law representations. Okay, okay, sure, good, good. Autoencoder. Yeah, autoencoder. I was going to talk about that only, but then it's going to. I mean, we can have a discussion about that after the session also. No problem. Okay. So let me just now I've got to implement this, right? This is something that I have to implement. So, like all machine learning scientists, I'm also a very lazy person. So of course I'll use a pre-trained network. I'll use a pre-trained network to do my job. And basically there's this library. Okay, where is it? Yeah. So when I was discussing libraries, I skipped this library, right? So this is a library uh, which is not a very famous library, but it is mainly for facial recognition, right? It is like the OpenCV of face recognition. It contains everything related to face recognition. Like you can detect faces, you can turn faces, you can do a lot of stuff. So this contains the pre-trained neural network. Pre-trained neural network with respect to the pre-trained neural network that I was talking about, that with the triplet loss. So let's just see. So we covered till this part of the code. Now we have this part, right? You have your encodings. If you guys want to do, if you guys want to install this, just write pip install in your terminal. Pip install face recognition, right? Yeah. You need to have dlib and all. That's right. Even I had that problem during the installation. Otherwise, you can go to their GitHub repository and you can clone it from there and do it. Right? So now I'm continuing with this. Okay. Okay. So let's start with the. So now let's see this. So this is your. So now you have understood the concept of embeddings. You have understood the concept of encodings. So what is happening here? This is the library. And this is face encodings. Barack image I1. So how many of you guys don't know NumPy here? Anyone who doesn't know NumPy? Yeah, Prasanna, I can use Collab, but I will have to upload them to the upload the images to collab. So it was easy for me to do it on a local system, but when I'll be uploading it on GitHub, I will provide the images side by side, so you won't have any problem with that, right? So anyone who does not know NumPy here, okay, okay, so that's what, because there was a major. So see what we're trying to do. Oh, we had these coordinates here, right? We have these coordinates here. What do we have to do? We take y1 goes to y1 plus h1, x1 goes to x1 plus. What are we doing? We're basically clipping x1 here to x1 plus w1 here, y1 plus y1 plus h1. We're clipping this portion. We're cropping out this portion. We're feeding it to this neural network here. This is the neural network. And then we're converting it into a NumPy array, right? It is already a NumPy array, but just to be sure, I've done it into a NumPy array. Then I'm storing it in Obama encodings. Let's just see, let me just print out the shapes for this. So you see the shape here is 128, just like I was talking about, right? So this is something that is pretty cool, right? I mean, this is a very good library. It is, in fact, I was reading this article on Medium, and it was rated like 16 or 17 amongst coolest GitHub repositories for machine learning. So it is a good library. Let's do the same for. So have you guys understood what I've done in this code here? Have you guys understood what I've done in the code here? Okay. So let me just viewers have dwindled, but no problem. We're going to go through this. We will be able to. So I'm doing the same for Trump, right? Let's just run and see this. Where is this image? So it is here. So you can see. I mean, this it's a really good face detector because you see, it has ignored his hair, and it has ignored a lot of. It is exactly cropped out his image. It is exactly cropped out. That is the best part about OpenCV, is that it is so perfectly crafted that you will have no problem in doing your computer vision projects. So let's start. So I'm doing the same to Mr. Trump, right? Then mm, let me just apply. So okay, we have our shape here. We have a shape here, and now I am storing it in a dictionary, right? I hope you guys know what a Python dictionary is, right? You guys know what a Python dictionary is? Okay, sure, no problem. Okay, welcome back, guys. Now I'm storing it in a Python dictionary, all the encodings. So for the guys who who had left the chat, this is basically this is my neural network. This is my neural network, and I am feeding it the cropped image. And then I'm taking these encodings, so you can see the shape of these encodings. So, right? Is it okay? Okay. So I'm doing the same for. So I'm doing the same for Trump, and then I'm storing it in a dictionary. So now let's come to a very important question, right? How are you going to detect multiple faces, right? So this is the picture that I've used, right? So you have both the faces here. You have both the faces here. You have a face of Donald Trump and you have a face of Barack Obama. And now we want to detect both the faces. So what do? We take the target image, we convert it to black and white. So whenever you're doing it you're applying a Haar cascade, convert it into black and white image. Convert it into black and white image. Then we applied detect multi-scale, right? Black white target image, you know these two parameters, then we are taking faces, right? Let me just run and show you what's happening here. Okay, so here we are. You have these two faces here, right? So what is happening is that the faces part represents, gives me two quadruples, right? Gives me two quadruples, and I iterate through these quadruples, and I am plotting for each one of them, right? It's very simple. It's just that you see this line of code is used for one face. I'm just iterating through these faces. That's all. You know this, right? So when we can go and check. See, this is what is happening here. So you guys remember x1, y1, w1, h1, right? It's giving me both the faces, right? So are you guys following me here? You guys are following me, right? Okay, okay. It becomes very difficult because your chat screen is appearing on another dialog box, then your screen sharing in another. So okay, sure. I'm starting my screen share again. Okay, let's go. So let's try to print the embeddings. Oh, I did not run this. Okay, so same concept, dictionary here. I have a dictionary, then I run this and I get all the embeddings. Okay. Now comes the part. Now see, we have detected faces. Now we need to find the embeddings. We need to find the labels, right? We need to label both of these people here. That is going to be our next aim. So let's start. Right. So now, if you want to, if the count code would seem a little bit intuitive to you, right? Is it's first line? We take one bounding box, we plot that bounding box on the target image. Then we crop the target image. So for example, in this case, we're going to crop Donald Trump's face in this photo, and then Donald Trump's face in this photo. And then we call we pass it to the neural network. We take the temporary encodings, that is the encodings for this particular bounding box, right? The encodings for this particular face. And then for word in picked dict.key. So what is happening in this line of code? For each of these characters, right? For Mrs. Clinton, for Obama, for Trump, we are iterating. What do we do after iteration? We calculate the Euclidean distance. Euclidean distance is nothing. What I'm doing here, I'm calculating the difference. Then I am taking their magnitude and I'm dividing it by 28 and returning. That's all. Right? Are you guys following me till here? What is black white target again? Okay, I'll tell you. Wait a minute. Are you talking about this? Black white target image is nothing but basically we're converting the target image into a black and white so that you can perform face detection. Or the start of the webinar, I said that whenever you're going to perform facial detection, then you need to convert it into a black and white image, right? Did you understand it? Okay. How about face dot detect multi-scale? Yeah, it's the same. So So that's what I'm doing here. See, face it or target image. These two parameters I told you earlier, and these are returning the quadruples. These are the quadruples. So these are the coordinates of the bounding boxes, right? Okay. Okay, sure. Okay. It's actually quite cool. So did you understand this Euclidean distance definition? Have you guys understood it? Did you guys understand the Euclidean distance definition, or do I need to explain it? Yeah, good. Okay, sharing my screen again. Okay. Okay, let's start. Now, let's come to this portion. So initially, I told you what was the main objective of our neural network. It was to make sure that the anchor and the positive image and their Euclidean distance is minimum, right? That is what our neural network ensures, and that the difference between an anchor and a different image is as maximum as possible. So what do we do? So if anyone can tell me what I've given you value with, I've given you a value of all the embeddings and their corresponding labels. So if there is, let's come back here. First of all, we define two variables, that is the minimum Euclidean distance and the minimum label, right? Then we calculate the Euclidean distance for each of the encodings. Each of the encodings, we calculate a Euclidean distance. Then we want to find whether this Euclidean distance is less than the minimum Euclidean distance. Wait a minute. You guys are able to, okay, so more people are joining the chat, right, guys? You guys are able to understand till now, right? So we want to find whether this distance is less than the minimum distance that we have found out till far. That is, we are trying to find out the minimum of the Euclidean distance between these encodings and for all the encodings in this dictionary, right? The minimum you for example, if so, we find the distance and we find the minimum Euclidean distance. If this distance is less than the minimum Euclidean distance, we store the minimum Euclidean distance and we store the minimum label, right? So word is basically the label. The Euclidean distance is the distance of the it is the minimum Euclidean distance till now, right? So again, very clear. Embeddings of the same person will have minimum Euclidean distance, right? So now we are iterating through our database, we're iterating through our encodings, and then we find out there is a there is a the label which has the minimum encoding. Label has the minimum encoding. That label is the label for the bounding box. If you understand it. Are you able to understand? What about the other guys? Arvind, Victor, and okay. Basically, the same concept. That's what I'm trying to implement. Very simple. I'm just trying to find out the minimum. Okay. So say for Donald Trump, but for the left image, So for the left image, this image, this his encoding will be less than the encoding of a less than the encoding of a it will be it will the minimum equilibrium distance will be with this label, right? That is what we want. The same we want the same for Obama's encoding also. So let's just see. Let's just so now we have our minimum label, right? I have iterated through. This is basically my iteration. At this point I end because my indentation ends. Then this is a very important line, right? So let's just debug this one by one. CV2.putText. What does putText do? PutText is basically putText is nothing, but it's basically you have to write your text, right? So if I'm going to label, I can't I can't like write it directly on the image. I have to use the putText function. What it is saying? This is the target image, the image on which you have to write. What are the wordings that you have to write? And this is the coordinate of the leftmost position from where it will start writing. Right? So x1 minus 15, y1. So can anyone tell me which portion of the bounding box this is going to be? Can anyone tell me which portion of the bounding box that is going to be? Left and left. Okay, okay, I'll do that. In fact, I'll just paste it in the comment box if you want to. If you want to, left bottom, right? That is where I'm going to write my write my because look, y1 plus h1. So this is basically your bottom, and this is my left. So yeah, so this is the starting coordinates of my text, and this is the so this is like you have you have Times New Roman and Word. This is for OpenCV. So this is a commonly used. This is called font Hershey simplex. 0.55 is the size of the text, right? It is just like MS Word. 0.55 is the size of the text. This is the color in which I will write my text. And 2 is the thickness of the line text. This is the type of line that I will draw, right? So, for example, when you're using Word, you have word art, right? You have different type of arts. The same way, you have different type of line styles. Anyone who did not understand the put text function, right? Anyone who did not understand the put text function, right? Other guys, other guys. Okay, yeah, kind of. Which images are you talking about, Tosin? Yeah, yeah, right. Yeah, kind of. Actually, they don't use OpenCV to write, uh, but I don't know. Maybe they might use. Yeah, because OpenCV, I mean, the font that we write with OpenCV is not so good. It's it's very like it's very old type. So I'll just show you how the end results come. So you have understood, right, what I'm trying to do. I'm taking a bounding box. I'm searching in the entire dictionary value for which it has the minimum Euclidean distance, and then I'm displaying that value. That's what I'm doing, right? Have you guys understood it? Okay. I'll just show you the result right now. Sorry. Again. Okay. Okay. right? So this is our uh, wait a minute. Oh, I did not run this. Oh, sorry. My bad. I did not run this. So, okay, should come now. Okay, so you can see this right here, right now. Can you see it? So this is saying Donald Trump, and this is saying Barack Obama. It has correctly matched. So this is what is the main essence of facial detection and verification. Right? This is a very this is the main essence of what we're going to do. And did you see it? Nice. So did you guys like it? If you want, I can show you again. Right? Wait a minute. I'll show you. So I mean, you can change the format here, right? And in fact, you can see that both of them even have different emotions. So in this face, he's smiling. This face, Barack Obama is smiling. And in this face, he's frowning. So it's also able to capture difference in emotions. And you see the orientation also. His head is shifted towards the right, here it is shifted towards the left. Still, it's able to do. Donald Trump, he has the same face all the time. So in this, you can see his eyes are looking downwards. It's looking upwards. Still, it's able to recognize. So that's the beauty of this network, right? It's so perfectly trained that it works out. So that will be about how to do it in real time video analysis. So I will cover that. Right? So what you can do is that you can start reading it in frames, right? So I haven't done that in the notebook because I didn't find any video, I mean, of them together or anything. It was not very good quality. So what you can do it in, I'll show you the code. Wait a minute, I'll show you the code on how we do it. So this is something that I did, right? So this is how do you want to do it? So I'm going to wait a minute, I'll show you. Yes. Wait a minute, I'll show you. Okay, don't worry. So, person, I'm not able to find it in the in how to do it in the video. What you do is basically you create what is known as a video capture object, right? So you create a video capture object, and then I'll show you how to. I'll explain you how it's happening here, right? So this is what you do in Python. What you do is you first create a video capture object, right? And then you specify the path of the file, right? You specify the path of the file, and what you this is, see, he has created this video capture object. Okay, right? Just I'll send this link. Wait, you know, and in fact I'll explain it. Let's just take 1 minute. So what is that your look, this is for your, if you have a video file, if it is your webcam, then just do this to 0, right? If you're using a webcam, do this to 0. Otherwise, use the source path, then see if the camera is opened, and read until the video is completed. So this will automatically happen, right? So return equal to true. So the see the red, the so you first, what you do is you do a cap dot read. So frame is equivalent to the image, right? So basically video is nothing but composed of frames. So frame is nothing but your image, and just apply the operations that we applied here to an image to this frame. That's all. You do that frame, then you display that frame. That's all. That's all you have to do, right? In fact, you can also write it in a video also. You can write it in AVI file. Okay. Okay. So that's it, guys, for the webinar. Right. Okay. Yeah. Okay. Yeah. I'll put them online. I'll put them. No problem. That's of. Oh, yeah. No problem. No problem. Thank you for attending the webinar till the end. I know there were a lot of glitches because I'm using Hangouts for the first time, and I didn't know that like you couldn't record. You can record on Hangouts, but it becomes quite a problem. If you can mute, you can unmute if you want to. Can't unmute this. Okay, I don't think you can, right? So any problems, any problems that you faced, you can ask. Any doubt that you have. Yeah. Okay. Sure. No. Okay. No problem. So yeah. So there is this study jam. Are you on the Google groups? Are you on the Google Hangout group, the earlier one which was created? I've put a Google form on that. I'll just send you the link. Uh, you guys just enter your name and what you did in the webinar and all, and what was taught and all. I mean, it's just like, I'll send you the wait. Okay, some of the guys here did ask about. I'm sorry, guys. For those who were. Wait a minute. I'll send you the form. This is the form, right? So you fill this form, and you fill this form, and it's about they just want to measure the attendance in the webinar. If you want to discuss anything else, we can discuss. Let me take a screenshot of this. Yeah, sure. Okay. So I'm ending the call, right? Yeah, okay, sure, no problem. Basically, I'm not sir. That I'm a second year student here in Delhi at NSIT. So, what about you guys? And if you want to introduce yourself, I should have done this at the starting. Oh, good. Even I am from Chennai, University of. Is this US? Ocean? Are you staying in the United States? Oh, okay. Good. Nice. That's great. That's great. Lot of. I mean, it's pretty good. Meeting international students. Yeah, Prasanna. Even I am from Chennai. Uh, yeah, sure. It's been nice meeting. I think it's a very good initiative by Udacity. Oh, so I don't have a WhatsApp group. I basically have a Telegram group, right? Which is kind of inactive right now. But because or in Slack, no, I don't have. I'm not the leader of any group on Slack. So you can join two groups of which I'm part of. One is and write it down. There are good groups. Like it's quite an active group. Hashtag SG Genesis. There is one group. This is one group. Another group is side projects. Side projects. Sorry. Side projects. So I mean, this Genesis group is like good because it's like really active, and these people keep a meet at least once a week. So you can join them. Okay. So should I end the call? Okay. Hmm. Sure. No problem. Okay. Bye. Bye, Prasan and Osan. Okay. Bye.